All right. Let's see what I got here. I think I got a verse for today. Let me find it. Oh, yes, this is 1 Chronicles chapter 29, verse 11. It's from the prayer of David. It says, "Yours, O Lord, is the greatness and the power and the glory and the victory and the majesty, indeed everything that is in heavens and the earth. Yours is the dominion, O Lord, and you exalt yourself as head over all." That is 1 Chronicles 29:11. I'll begin with a word of prayer. Heavenly Father, we thank you again for this class. I thank you for this opportunity we have just to meet and study your creation. We thank you for manifolds and league groups. Help us to understand a little bit more about them today, Lord. In your name I pray, Lord Jesus. Amen. All right, so not enough. How many? I don't know. That's a good question. Oh, wait a minute. That's chapter 8. We're in chapter 7. Let's stay where chapter 7 is where we're at. Okay, so last time we introduced league groups and league group homomorphisms, right? And we more or less proved theorem 7.5 that every league group homomorphism has constant rank, which is super nice because that means we get all that constant rank goodness from the submanifold chapter in play, right? So the next subsection here in John Lee's chapter 7 is on the universal covering group. And I don't want to write too much down there because that's a very, very topological section. Let me just talk about what is the universal covering group. So here's the theorem 7.7. It says, let G be a connected Lie group. Then there exists a simply connected Lie group G tilde called the universal covering group of G that admits a smooth covering map pi that goes from G tilde to G that's also a Lie group homomorphism. So listen, to carefully define simply connected would take us far afield here. Okay, like we don't have a definition for simply connected. Much less, I mean, we don't have a definition for connected at the moment in this course, right? I mean, I can give you a definition for connected. A set is connected, I think I told you guys this last time, if and only if it does not exist, it does not permit a separation. So a separation is a pair of open sets whose union gives you the whole set, and yet they're disjoint. If that's the case, if you have a separation, the sets forming the separation are both open and closed. See, because if the union is the whole set, that means they're each other's complement. So if the complementary set's open, that means it's closed in the definition of topology. A closed set is one whose complement's open, right? So if you have a set which is connected, that means that there are, so another way of saying a set is connected is to say that there exist, another way to say a set is disconnected is to say that there exist sets which are both open and closed in the set, and yet are not the whole set or the empty set. This is often a proof technique which is used. To prove something is connected, you show that the only sets which are both open and closed are the whole set or the empty set. So, all right. Anyway, simply connected, we have an idea about it from Calculus 3, right? It's like that idea that you can deform loops to a point, right, without getting hung up on something. So apparently, with a Lie group, it doesn't have to be that way. There can be, there can be some kind of hang up. But this is saying that, hey, there's this universal covering group which is simply connected. And, the examples. Well, I said I wasn't going to write, so let me stick with my conviction to not write. Okay, because I sometimes say that and then I start writing and then I regret. But example 7.10, he gives the example of like Rn maps to Tn, so you can basically take an n tuple in Rn, x1 through xn, and map to e to the 2 pi I x1 all the way out through e to the 2 pi I xn, that is a Lie group homomorphism, which is a smooth covering map. So basically, Rn is the universal cover of the N torus. So like in Rn, you can take any loop and deform it to a point. You kind of know that. I mean, we haven't carefully defined smoothly deformed to a point, but that's something you could do in topology once you get all your ducks in a row. That's what homotopy is about. It's about talking about deforming one space to another in a careful way. So you need like continuity of the Cartesian product to make that rigorous. And so the universal cover of the N torus is Rn. The universal cover of the non-zero complex numbers is just the complex numbers. The covering map is the exponential. And let's see here, what else can we say? That's pretty much it. So that's just a quick foray into that. So let me give you some theorems on Lie subgroups here. So this is here we go. A Lie, I guess I probably should give you a definition, huh? A Lie subgroup of a Lie group G is a subgroup endowed with a topology and smooth structure, making it into a Lie group So this is pretty much what you told me last time, Jeff, I think. Making it into a Lie group and immersed. Submanifold of G. So as we kind of discussed, the immersed submanifolds are slightly unpleasant, but the sort of most general view, so that's what he takes as his default view of what a submanifold is an immersed submanifold. But as we talked about, the embedded submanifolds have kind of nicer properties. The properly embedded submanifolds are even nicer still. Okay, so anyway, proposition here, 711, says let G be a Lie group, H a subgroup that's also an embedded submanifold, then H is a Lie subgroup. So let me try to summarize that. Proposition 711 says that if you have H a subgroup of G, like a subgroup, all right, and embedded submanifold. So if you have that, if H is a subgroup and an embedded submanifold, then H is a Lie subgroup. Okay. So what's that saying? It's just saying that if we restrict the operation of the multiplication and the inversion for the group, they're smooth maps, right? And that's going to be true because you're assuming that it's an embedded submanifold. And if you restrict a smooth map on a manifold to an embedded submanifold, we have theorems that guarantee the smoothness of such restrictions. And let's see here. I think ultimately he says it rests on corollary 5.30. Not much to see here. Proposition 7.12. Suppose G is a Lie group, H is an open subgroup, then H is also an embedded Lie subgroup. So let's see here. Yeah. Oh, this is going to be lemma 712. So lemma 712. So H subset of G. So this is, let's say, open in the topological sense, right? Open subgroup then H is an embedded Lie subgroup. In addition, also H is closed. Hence, it is a union of connected components of G.
Is the word embedded here important, or does that just mean subgroup, subset?
Embedded? Yeah, well, it refers to the
Just trying to see if there's a difference between 7.11 and 7.12. Other than
well, the assumption here is that this is a subgroup and an embedded submanifold. Here, the assumption is it's an open subgroup.
so maybe part is something else.
So open is stronger than embedded. There are embedded submanifolds which are not open, but I think every open subset of a manifold is an embedded submanifold with one of our theorems. Embedded by the Yoda map, right? Because it's a smooth submersion, if I remember right. We're still in the part of the semester where I haven't forgotten these things. That's good. Hence, H is closed, hence is a union of connected components of G. So we are getting a little topological here, but I think it may be worth our while to like try to sort through the proof of this lemma. Let's attempt it, and we'll see if we can hack it. All right, let's try the proof of this lemma. So we're page 156 of John Lee's book. Here's his proof. H is open and G is assumed. All right. All right. Hence, it's embedded. Which means what? By proposition 711, I think. Oh, no, he's not going to go that way. He said it's embedded by proposition 551. Okay, so he's going back to chapter 5 and the submanifold theorems back there. So if it's open, it's an embedded. Again, I think by the Yoda map. And yeah, really. In addition, every left coset. What's a left coset? So this may be news to you guys, right? But a left coset is GH. So what that is the set of multiples of elements in the subgroup. So this is a left coset. You take the subgroup and you multiply by, G is fixed here. It's a specific element of the Lie group. And G times the subgroup gives you what's called a coset of the group.
For some H or all H?
H is fixed. H is the given subgroup here. But that H varies. So it's, yeah.
The G is fixed. So
But he says every left coset GH is open. It's open in G since GH is actually equal to what? It's equal to the diffeomorphism L sub G acting on, it's the image of the subgroup under the diffeomorphism L sub G, right? It's the image of the subgroup under the left multiplication by G map, which is a diffeomorphism, which means it's an open map. And you guys know that if we have an open set and we have an open map, that by definition, open maps to open. But anyway, more to the point, the inverse of the L sub G map is L sub G inverse, which is itself continuous, and the inverse image of a, continuous inverse image of an open set is open by definition. So anyway, we have this is open. Then what? And he says, okay. Now here's some group theory for you guys. It's kind of a bizarre bizarre place to first see the factor group, but here it is for you. So the factor group, guys, it's the set of all cosets. So eventually in your abstract algebra course, which you guys have not had, right? Okay, yeah. So this is the set of all cosets. That's the set of all cosets. So when you study this in 421, you'll prove that membership in the coset forms an equivalence relation. So like two elements in the group are equivalent if and only if they are members of the same coset. So this forms an equivalence relation. Every element is the member. Every element is equivalent to itself. That's reflexive because anyway. So you can prove that that's an equivalence relation, which means it's reflexive, symmetric, and transitive. And then that means that the cosets themselves are in fact the equivalence classes when you study this, and the equivalence classes partition the group, right?
They're the entire equivalence class?
Yeah, right. Yeah, so like GH is the equivalence class. The equivalence I'm talking about is like X is equivalent to Y if and only if there exists G in G such that X is an element of G, H, and Y. This is a stupidly clumsy way to express this equivalence, but that's just how it came out of my brain at the moment. There's like an easier way to say that. What that's really saying is that you could write Y as equal to like I think it's equivalent to just saying that there exists H such that Y is equal to X times H. I believe that's pretty much the same. Am I right, Ernesto? You're closer to it.
Yeah, that's it.
Right. So that's there exists an H such that Y is equal to XH is another way I could define the equivalence that would be less weird. Anyway, the point is that these cosets, they partition the group, all right, into disjoint sets, right? Like the cosets themselves are disjoint, okay? And in other words, the G is equal to a union over, G and G of GH. And these are partition of G. Anyway, I'm getting too far into this. Anyway, so it says because G mod H is the union of the cosets of H, other than H itself. Oh, I'm a dummy. That's not even what he's talking about. I'm just a moron. He's not talking about this. He's not talking about the factor group. I'm an idiot. He's grief. He's talking about this G minus H in my notation. So this is, but of course that other notation. So this is G and G such that what? G is not an element of H, right? That.
Isn't the slash the other way in his notation?
Yeah, yes, this is fair enough. Fair enough. I hate that notation, so I don't want to see it. All right. Yeah. You're not wrong. But that is the union of the cosets of H other than H itself. And it's open. Hence it's open. All right. So this, to see that this is open, this is going to be this. Okay, it is relevant to what I was just saying, So like G minus H, you could say is the union of, you know, well, you could just, it's kind of stupid, but you could say G in G minus H of GH. That would not be wrong. It's all the cosets that aren't obtained by the identity coset, the coset which is, you know, represented by the identity. But anyway, the larger point is that every one of those cosets is open. And so this will resonate more with you guys. So you're looking at a union of open sets, which is therefore open. And so the complement of H is open. Therefore H is closed. And that is what we said over here. And he says, hence it's a union of connected components of G. Hence it's a union of connected components of G. I'm not sure quite how to unpack that for you guys at the moment. Let's go on. So yeah, what's that?
I said it wrong.
Oh, you said a wrong thing. Oh no, this was this was not an actual question. This was some sort of computer architecture comment, wasn't it?
No, it was a question, but
Oh, it was a question. It was just not a.
it was not an intelligent question.
Not an intelligent. Well, that doesn't even make sense. There's only intelligent questions.
Hey, one minute, want to hear me ask? Another question of the day?
Go for it.
Dr. Cook, why are you laughing?
There are questions.
Oh man. Oh, I'm seeing stuff. Okay, here we go. So, if G, this is actually important. Well, I think it's important. I don't know how important. So, if we have S a subgroup, a subset of G, this is not necessarily a subgroup. Okay, just a subset. Then the subgroup generated by S is the smallest subgroup. Let me say smallest subgroup H of G, for which S is a subset of H. So this is the notion of a generating set for a group. All right. You've seen this idea in like linear algebra. A generating set is a set that for a subspace is what? It's a set whose span, you know, forms a subspace. And like the span of that set is the smallest subset. The span of a given set of vectors is the smallest subspace, which takes that subset as a subset. That is also true. So you can think about this in terms of linear algebra, even though you guys don't have group theory yet. Okay, so let's see here. Your exercise 7.13. I'm not saying it's your exercise. I'm just saying this is an exercise I might assign you. I don't know. Let's read it together. Given a group G and a subset S of G, show that the subgroup generated by S is equal to the set of all elements of G that can be expressed as finite products of elements of S and their inverses. Yeah, I don't think I'm going to assign that. That feels very much like a group theory exercise, which is not this course. All right. Proposition 7.14 says the following. Let me try to pick up the pace in here. I'm not trying to spend too much time on this material. Suppose G is a Lie group and W is any neighborhood of the identity. So G, a Lie group. And so here's the Lie group. Here's your eins element. And then W is one of these deals. Some neighborhood of the identity. Then what do we get to say? Oh, not just any. It says W is any neighborhood of the identity. Oh, well, that's very generous. any neighborhood of eins element, okay, then A, W generates an open subgroup of G. B, if W is connected, who on earth uses a disconnected neighborhood of the identity? What's wrong with these people? Good grief. If W is connected, it generates. Who works with unconnected neighborhoods? Ew. It generates. I'm repulsed by that. It generates a connected, but then again, I haven't taught reals, so what do I know? A connected open subgroup. Okay, well, I feel better. So if a neighborhood is as it should be, then it generates a connected open subgroup, in fact. And then, ooh, look at this one. If G is connected, bless you. If G is connected, then W generates the whole group. So the proof rests on the exercise you guys aren't going to do, so I'm not going to really go through the proof that much, but essentially he just looks at like, well, let me just give you some snapshots of what goes on in the proof here. So he's looking at AB, which is defined to be like AB, such that A is an A and B is an B. Okay, he defines that. And he defines A inverse to be the set of inverses of elements of A. So that's an interesting notation, I suppose. So with that, he then talks about W sub K being the set of all elements of G that can be expressed as the product of K or few elements. It can be expressed as the product of K or few elements. So it's he's using W union its set of inverses. All right, so WK is formed K or fewer elements in the union of W inverse by the exercise that we're not going to do. WK is the union of all sets, WK as K ranges over the positive integers. Well, H, rather, the subgroup which is generated is the union over WK. And then he argues that W inverse is open because W inverse is nothing more than what? It's the inverse map. It's the image of the inverse map on W. And if the inverse map is a smooth map, it's a in fact it's a diffeomorphism, actually. The inverse map is, because it's smooth with smooth inverse. It's its own inverse, right? Inverse composed with inverse is the identity on G. And as such, it's a diffeomorphism. That being said, that means that W inverse is open, W is open. And then let's see here. And then he does some kind of sneaky argument here. W1 is W union W inverse. And he says for each K, you've got WK equal to W1 times WK minus 1, which by the exercise we're not doing is, I'm really writing a lot of details for not writing details. W1, my bad, of the left multiplication by G of WK minus 1. And then he says, because each LG is a diffeomorphism, it follows by induction that each WK is open, and hence H is open. All right, and then he gives some arguments to support the other conclusions, but Anyway, I don't think I've done justice to the proof, but I'd like to point out to you that the proof is not that difficult, actually. All right, these claims, it's not that. These are not like super technical. Proposition 7.15, well, he says, okay, so if G is a Lie group, the connected component of G containing the identity is called the identity component. So, so you can kind of think of a Lie group something like this. So the Lie group has to have these connected components. And what I mean by that is, like in one of these, you've got E. Eins element is in there somewhere. And this proposition 7.15 says let G be a Lie group and let G naught be its identity component. So this is G naught, all right? He says then G naught is a normal subgroup of G, and it is the only connected open subgroup. So this is a topological result. So this is not, so G is going to be equal to a union, let me just say over alpha of G alpha, where these are the connected components. So you go through this long litany of logical lemmas and so forth to build up this concept of connected component in topology. But basically, these are like the largest connected sets that you can form, right? You just keep making them, you make them as big as you possibly can. And then it'll follow that, like, for disjoint alpha, these are distinct. So like my picture has G1, maybe it has, I've drawn it as if G has only got apparently 5 components, right? So you can't make it bigger, because if you did, then that component itself would have a separation and it wouldn't be connected. All right, so like, so the connected components are, I think every one of them is both open and closed because, I don't remember the topology well enough to just tell you off the top of my head, but it's not surprising that this is the only connected component which is a subgroup, because the identity is only in one of these. So that's the only one that can be a subgroup, because you need the Eins element to be a subgroup. And that's what proposition 7.15 is saying in part. But it's saying more than that. It's saying that G naught is a normal subgroup. And he also says that G naught is diffeomorphic to G alpha for all alpha. All right. So he's also saying that every
Are the G's here as big as they can be such that they're connected?
Yes. Right. That's more or less the definition of connected component. But you guys, have you guys got to that in topology yet? No, you're still in metric stuff.
We just defined topology.
Okay.
Yes.
Cool. Good. So anyway, all of the connected components are diffeomorphic. So they are, because, and the reason that has to be is, while these sets are disconnected, they are still connected in a sense by the left multiplication maps. See, like the left multiplication map is a bridge, right? Because I can left, if this is a particular point x1, and this is a particular point x2, and this is a particular point x3, this is a particular point x4, well, the left multiplication by x1 goes to here, the left multiplication by x2 goes to there, left multiplication by x3 goes there, left multiplication by x4 goes there, right? So there's diffeomorphisms that map the identity component to the other components. So they end up having to be diffeomorphic, yeah.
If they're diffeomorphic, would they still not be groups or subgroups? G3.
So they.
It doesn't have the Eins element.
It doesn't have the Eins element. They are. I believe they're submanifolds. So there's submanifolds of the Lie group which are not sub-Lie groups. So they've got the right smooth structure, but they don't have the right group structure.
So would we want to?
I would say this.
Go to G naught instead of going to like G2.
Well, it depends on what we're after, I suppose. But G naught is also a normal subgroup. So when you guys take group theory, one of the things you'll learn is that in order for that factor group to actually be a group, you need H is what's called normal. A normal subgroup is one for which the left cosets and the right cosets are equal. Or you could say it's closed under conjugation. And so G not being normal means the factor group is in fact a group. I guess that's all I got to say here. But my intuition is this, though, that while the connected components are not, they're not groups, they're not subgroups, there's probably like a non-standard operation that you could build on these things to make them into the subgroup. Like basically, since they're diffeomorphic to the G naught, like you could like just basically, you could use the left multiplication map to like plaster the group structure over there if you were so inclined. But they wouldn't be subgroups because it wouldn't be the same group operation that you're restricting. So they wouldn't be Lie subgroups. But you could play such a game, I think. All right, so getting to the point here, proposition 716 is if you have a Lie group homomorphism. Oh, this one's huge. These are big. So proposition. These are example building propositions. You have F from G to H, a Lie group homomorphism. All right. Then the kernel of F, which I'll define for you guys, that's G and G, such that F of G is equal to Ein's element in H. So that's the kernel. That kernel of F is a properly embedded Lie subgroup of G. Properly embedded subgroup, I can't write today, of G, whose codimension is the rank of F. And proposition 7.17, also known as 7.17, is that if you have F going from G to H, a Lie group homomorphism, an injective Lie group homomorphism, then the image of F, right? The image of F, which is equal to F of G, such that G is in G, all right? Then what is that? Well, this is also, here's a better way to call it. It's just F of G, right? It's the image of G under F. Is a Lie subgroup. Lie subgroup of what? Of H. Moreover, F as a mapping from G to its image is Lie group isomorphism. You see, because if it's injective and it's onto, well, then it's a bijection, right? And if it's a homomorphism, it's constant rank, which means then that we get smoothness as well. Okay, so This gives us tons of examples, really nice examples. I remember this being important when I took a course on Lie groups. This is part of the reason I wrote this out. I know it seems kind of technical, but I feel like there will come a time when we'll be happy that we took a second to talk about this generating business. We're not there yet, but this will come back eventually if I stick with things. Maybe, I'm not sure where that is. I don't remember exactly where that happens, but then again, this is not a course on Lie groups. This is, Lie groups is just kind of something we're covering the basics of, right? You could take a course in Lie groups, like it's a whole, there's enough material here to occupy a semester, maybe more. Many things are known about Lie groups. I have like a whole Springer book, which is just Lie groups. It's like this thick, by an author named Neeb. Okay, so these examples, let me try to be crisp about these here. So A, you got your GL plus of NR. That's a subset of GLN R, right? That's an open subgroup, thus an embedded Lie subgroup. That's a Lie subgroup, okay? B, so basically it's going to be our list of examples again, right? The circle group is a subset of, the non-zero complexes. And so this is Lie subgroup. It's Lie subgroup of C star because S1 is embedded submanifold of the non-zero complexes. C, now it's starting to get interesting. SL, this is a new one I think for us. Well, I think I threw it out here for you guys a while ago, but I don't know if we've talked about it recently. SLNR is the n by n real matrices with determinant 1. So you guys tell me, why is this? So here we have A in, how do I want to look at this? Yeah, A in GLN are such that determinant of A is equal to 1. All right, so let's unpack this a bit. Yeah? Mm-hmm.
Do we even need to say A is in GLNR because we're going to say determinant equals 1?
Oh, yeah, but we want to, the thing is we want to look at this.
Say that's a sub.
We want to look at this as like a subset of GLNR, but you're not, yes. You could just say A in Rn by n.
But we're doing that.
But I want to think about F, a mapping from, the general linear group of n by n invertible matrices to the non-zero positive real numbers, right? Those are Lie groups, right? By example 1 and example 1 with n equals to 1. There's a lot of, example A. Oh, wait a minute. Well, this is the positive one, positive determinant ones, but this is just everything. So, okay, anyway. The point is, what happens if you take f of AB? You've got what? I'm defining f to be the determinant, okay? So let's suppose f is the determinant. Well, the determinant of AB is the determinant of A times the determinant of B. So that is f of A, f of B, right? which shows you that F is a group homomorphism, right? It's a group homomorphism from matrix multiplication to numbers, right? And notice that SLNR is what, actually? Can you recognize what it is? It is the inverse image under the determinant. Let me just get to the point here. It's the kernel of F. It's the kernel of the determinant map. If you want, I could use this notation. It's the inverse image of the determinant map of the number 1. It's the set of all matrices whose determinant maps to 1.
And, 1 is our eins.
Yes, 1 is the eins element in the positive reals. It's the identity. So, let's see here. Lie group homomorphism. So the question is determinant a Lie group homomorphism? So I showed you it's the homomorphism. I guess I also need to make sure it's a smooth map. But we argued the determinant's a smooth map in a previous lecture, right? So that makes SLN a Lie subgroup. All right, it's a Lie subgroup of GLN. Then the question is, what's the rank of the determinant map? Let's see here, what's he say? He says, because the determinant function is surjective, it's a smooth submersion by the global rank theorem. So SLNR has dimension n squared minus 1. Ooh, sneaky. So he claims, right, his claim is that the determinant mapping from GLN R to R is surjective. Right, and then we had the global rank theorem. What did that tell us? Yeah, you guys will have to tell me because I don't have that part of my book with me. I've gotten lazy. I'm only bringing the printout I'm working on.
On the one that if it's a smooth, the rank is equal to the dimension is equal to the
So I want to say the rank of the determinant map plus the
rank theorem.
The dimension of the, determinant map GLN R is equal to the dimension of the, what's the dimension of GLN? Well, the dimension of GLN is n squared. So we have n squared is equal to the rank of the determinant, which we don't know. And then over here, he's arguing that this is 1. Now, he hasn't really proved it. He just claims that the determinant is surjective. Can you prove the determinant is surjective? In other words, give me an n by n matrix whose determinant is invertible, an invertible matrix whose n by n determinant is equal to t.
with being in the first sentence and everything else.
T and then diagonal 1.
Oh yeah. And everything else here.
So just t here and then ones.
Or T anywhere on the diagonal and 1 everywhere.
Well, we just need one matrix. So that is zeros elsewhere. I think that works, right? Certainly we can construct that as an n by n matrix. And now here, this is for t in R star, right? Of course, the one thing we can't do is map to 0, right? Because we don't have any determinants. I mean, yeah. So yeah, I think this is reasonable. The determinants of surjection onto R star, and therefore the rank is n squared minus 1. If that's true, the codimension is the rank of F. What's that mean? The codimension is the rank of F. Did I do this right? I'm not sure I've got this right, guys. I'm sorry. I have a bad feeling. Oh, it's okay. Thank you, though. Yeah, SLN. So I don't. Something's mixed up in my mind. See, because the kernel, his codimension is the rank of F. But to say the codimension of the kernel is rank of F, that means that the dimension of the kernel is what? Supposedly, the dimension of G, right? Minus the rank of F, I think, yeah? Isn't that right? So like, for example, if the codimension was 1, then you'd have like 1 less dimension than G, I think. Is that right?
Isn't there a theorem in linear algebra that the dimension of the kernel plus the rank equals the dimension of the vector space?
Yes. Yeah, that's the rank nullity theorem. Sorry, I'm not sure why I'm confused. Oh, it's not the rank of the determinant I need. What do I need? Oh, I'm a dummy. So the rank of... why am I after the rank? I don't want the rank of the determinant. I want the rank of the... I want the dimension of the kernel of the determinant, So, yeah. Dummy. Me, not you. So what I should be looking at here is the rank of the determinant plus the dimension of the kernel of the determinant, right? That plus that should be the dimension of the domain. That's the global rank theorem. So we just figured out that the rank of the determinant is also the dimension of the image of the determinant, which we just argued is 1 because it's surjective. So that shows you that. Oh man. Well, that shows me that seems like the dimension of the kernel is n squared minus 1. Is that right? So then that's all I want. That is the dimension of SLN. So I'm done. I'm sorry. I'm doing something stupid in my brain. Hopefully it didn't hopefully not too much of that leaked out onto the board. Let's go on. It's done. It's been done for like 5 minutes. My apologies. All right, so next up here, we can look at he's got this handy dandy mapping from beta. This is a really neat map. I've studied this before. And it's a mapping from GLNC to GL2NR. And this is not an altogether obvious map, but basically the thing is, it's basically, this little mapping, M, let's say, this is my notation, M plus A plus IB, it's the 2x2 block, A, B minus BA. So that's the, if you will, the real Jordan form that corresponds to A plus IB. And so basically what you do with the n by n complex matrix is just take every complex entry and expand it as this 2x2 real Jordan block. And yeah, let's see here. So this is just to basically beta of, oh man, this notation is really hideous. Oh well. A11 plus IB11, and then A upper n lower 1 plus B lower 1 upper n, eventually n plus I, B, n. Anyway, so that's the, you like this what?
I always forget which one's on the left and which one's on the right.
Anyway, so I'm going to write it, instead of this, I'm going to just say it's the matrix of A11 plus I, B11, and then so forth. And over here, the matrix of A1n plus I, B1n, and so forth. Or here, let's be more civilized. This mapping beta, it maps the entry Aij plus Bij, no danger of confusion for the I and the I, to the matrix with M of Aij plus Bij. So this is n by n, it's in Cn by n, and this right here is in R 2n by 2n. And he says it's straightforward to verify that beta is an injective Lie group homomorphism whose image is a properly embedded Lie subgroup of GLN 2R, 2n, R. Thus, GLNC is isomorphic to this Lie subgroup of GLN G2NR. So anyway, the long story short of this mapping allows us to view the image of GLNC. All right, there is an isomorphic image. What that means is that there's a subset of real 2n by 2n real matrices which has all the same algebraic structure as the n by n complex matrices, and yet they're manifestly real. And as such, what's the dimension? Well, let's see here. The dimension, this had dimension n squared as a complex, like it's got n times n complex parameters, which is, so every one of those is, I think it's 2n squared is its real dimension. Is that right? We talked about this the other day. Yeah. Well, okay, so this space is bigger, right? This has dimension 4n squared, right? But if we looked at beta of this GLN C, that is a subset of this GL2NR. God, come on.